Alright, Assalamualaikum. Hi everyone. So today I will explain about the Bernoulli equation uh, to apply in a hydraulic system. So basically, I think all of you already learned this equation in a fluid mechanics class, but now we want to apply this Bernoulli equation in fluid power application, specifically in a hydraulic circuit analysis. Alright, so this is very useful relation to perform it in the hydraulic system because we can put some properties and we can look another properties using this Bernoulli equation. So its application allows us to size components such as pump, valve, and piping for proper system operation. And if we recall back on the Bernoulli equation, this is the simplest form of the equation of the Bernoulli. P over rho g plus v1 square over 2g plus z1 equal p2 over rho g plus v2 square over 2g plus z2. This can be taken into account when you want to analyze between 2 points at a fluid stream. Okay, so when this fluid stream is connected between 1 and 2, we can use this Bernoulli equation, right, to find the properties such as the pressure, velocity, or even we want to find the corresponding height between at point 1 and also point 2 here. Okay, so in a fluid mechanic or fluid power or hydraulic circuit analysis, basically we need to take into account the existence of the pump, the hydraulic motor or turbine, and also there are also losses between point 1 and also point 2. Right, so here when we want to include the hydraulic components, which is hydraulic pump, as I mentioned earlier, and also hydraulic motor, we need to put this and this into your Bernoulli equation. So originally we just put the equation like this one. So this is the pressure head form. So if you still remember the head form here, basically P over rho g, this is the pressure head. V square over 2g, this is your kinetic head. And this Z is your elevation head. So the difference between 1 and 2 is the change of this value. Okay, so when we put in terms of the analysis of the dimension, P over rho g, basically the unit will be in meter. V1 square over 2g also in meter, Z also in meter. So all will have the same dimension. That's why we use head. So head, this is the unit will be in meter as your SI unit. So in order to get the unit in meter, we must make sure that this pressure unit must be in a Pascal, this density must be in kg per meter cube, and this g is meter per second square. While for the velocity here, the units must be in meter per second. This Z must be in meter. Okay, so to make sure that you use a correct unit, because different unit will bring you into different answer. Okay, so now how to put this hydraulic pump and so hydraulic motor into the original equation here. So this is not in the head form, so this is the just in the one form of the Bernoulli equation. Basically we have several form of Bernoulli equation, but if we refer back to this head form, we can put also this as your equation, right? So now right, so this is P over rho g. Okay, P over rho g here sorry, P over rho g plus V square over 2g plus Z. Okay, at point 1 here, or at the input of the fluid stream here, you can put your head of the pump right? Because this basically give you the energy input to the system pump, so that it will increase or put some amount of energy into the system. That's why we put on the left side of this equation, while on the right side of the equation just put here the same things, P2 over rho g plus V2 square over 2g plus sec2. Then you need to add another two terms, which is the first one is the motor head here, right? So so this is the hydraulic motor head here, and then you need to put the losses pass through the fluid stream from point 1 to point 2. So these losses basically can be divided into two things, which is the major and also minor. Alright, so now your modified Bernoulli equation is P over rho g plus V1 square over 2g plus Z1 plus HP, which is a pump head here. While for the right hand side of this equation becomes P2 over rho g plus V2 square over 2g plus Z2 plus HM stand for the hydraulic motor head and also the head loss here, HL. Okay, so there are three terms instead of the original equation here, P over rho g, and also there's no other terms of the head such as pump head and also hydraulic motor head. So in order to calculate the pump head here, right, so what you need to do, okay, so this is the formula to get the head pump here. So this is WP, stand for the pump power, and you need to make sure that this is in watt. Okay, so this is the density, kg per meter cube. This one is gravity acceleration, meter per second square. This one is your volumetric flow rate. Okay, so this is volume flow rate. Unit is meter cube per second. Okay, so this is how to get your pump head. So for the motor head here, hydraulic motor head here, basically you can find through the specification of the hydraulic motor, but there is no exact formula when we want to get the value of this, okay, unless we use a sum calculation to find the motor head. So you need to find from the hydraulic motor power, and then you convert it into the head, right? And while for the losses also we can find it by go through the fluid mechanics class and find what is the formula for the major losses and also the minor losses. Okay, so here I will write it back at the proper equation. Okay, so if you use here P over rho g plus V1 square over 2g plus Z1 plus HP equal to P2 over rho g plus V2 square over 2g plus Z2 plus HM plus HL. Okay, so for the HP here, this is equal to WP, so this is in watt divided by rho GQ, while for the HL here can be divided into two, which is the major and also the minor losses. Okay, so for the major losses and also minor losses, you can look at this formula. For the major, FLV square divided by D2G. Okay, F is the friction coefficient, L is the length of the pipe, V is the velocity, meter per second, so D in the diameter of the pipe, inner diameter, and this is 2G, gravity acceleration. And while for the minor losses, basically is due to the connection, KV square over 2G. Right, so this is the formula, you can refer it. So to find the K here, you can refer to the table, also F. Okay, you can use the Moody chart to find the value. Okay, but in this class, basically, we're not focusing on how to get HL, how to get the HM here, alright? So we are focusing on how to apply the equation. So right now, if we want to ask you, maybe we will ask you during the fluid mechanics class, but this is the fluid power. We just want you to apply what we have learned during the fluid mechanics class into the fluid power application. So now we refer to another good formula for you. So this is the power, work over time, hydraulic power, which is P times Q, right? So the pump head here is equal to W divided by gamma Q. So what is gamma? Gamma is rho G. So another formula here, you can also write it as this gamma Q. So gamma is equal to rho G. Other than that, this gamma also can be represented by the specific gravity times with the density of the water times G. Okay, because this is your rho of your fluid. Okay, so this is just some revision from the fluid mechanics class. And then if you want to find other terms, you need to do some assumption. For example, assumption at the velocity. When you deal with reservoir, you need to make sure that it is approaching into zero, and then the pressure at the atmospheric pressure level, we just put as a zero gauge pressure. Okay, so now we look into other formula here, which is power is equal to torque times with the omega, right? So this is based on the output produced by the hydraulic motor. Okay, and also if we want to find the input from the pump, also we can use this formula. Okay, so and other things that you can use this formula is the things that is have a torque and also have some rotational movement. And then also the very useful formula is omega, which is 2 pi n over 60, where n is your RPM, rotational per minute. And then from the continuity equation, you can find this Q equal to area times with the velocity. Okay, this is some theoretical behind the Bernoulli equation applied to the hydraulic system analysis. So now we are focusing on this example of the hydraulic circuit analysis. Right, so I put a new page here. Okay, so this is the problem regarding on the hydraulic system. So if you look carefully here, we have a hydraulic oil tank as a reservoir. We have the strainer to filter out the contaminants. We have the pump here driven by the electric motor as your prime mover. You have the pipe here as your inside diameter is 2 centimeter only, and this is your hydraulic motor. So this problem basically wants you to analyze from point 1 until point 2, and you need to apply the Bernoulli equation to find parameter that it wants. For example here, it gives you the value, certain value here, which is the pump power, right, 3730 watt, volumetric flow rate. So this is also from the pump, output from the pump. So by using this also you can find the pressure produced, and this is the inside diameter of the pipe, specific diameter of your working fluid, which is oil, 0.9. So you can convert it into the density of the water, and the elevation between station 1 and 2 is 6 meter. Right, so what are the parameters that it wants you to find? Actually is the pressure. Find the pressure at the inlet to the hydraulic motor. So it asks you your pressure at station 2. The pressure at station 1 in the hydraulic tank is atmospheric. So this is your information, good, very valuable information to simplify your Bernoulli equation. And the head loss basically already calculated as the total losses here is only 9 meter, right? So you can put it in your Bernoulli equation. Alright, so after we understand this problem, now we will look to analyze from point 1 to point 2, and what is the component we have from point 1 until point 2 here. So this is point 1, this is point 2. So what is the component here? You have pump here. This is electric motor, and you no need to put into your Bernoulli equation because it already transferred into the pump. So you just consider the pump as our part of the Bernoulli analysis, and then you need to consider also the losses produced by this pipe. However, it already calculated just now in the equation. And at point 2 basically is the inlet of the hydraulic motor. So if you understand the flow of this process, so it is oil come from the reservoir here and then put into the pump, then go into the hydraulic motor, then hydraulic motor produce a power, and then the remaining fluid goes back to the reservoir. So it will be cycle here. Okay, so from 1 to point 2 basically no hydraulic motor. So in your Bernoulli equation, no need to put the HM term to represent the hydraulic motor. So don't confuse between electric motor and also hydraulic motor because it is different. Electric motor basically the input is electrical energy, while for the hydraulic motor the input is a fluid energy. But both produce the mechanical power output. Alright, so in order to apply from point 1 to point 2 here, we just write the fully Bernoulli equation, which already been modified. P1 over rho g plus V1 square over 2g plus Z1 plus HP. This is equivalent to P2 over rho g plus V2 square over 2g plus Z2 plus HM plus HL. Okay, so now you need to put your assumption here to simplify your Bernoulli equation. So the first assumption here is your HM is not include from point 1 to point 2. Okay, so you can cancel it out. Okay, and then number 2 here, your P1 is equal to 0. So this is already given in the equation, okay, because it state that this hydraulic tank basically experience atmospheric pressure 0 kPa. So you just put here as 0 kPa, so it will be 0 here. And then number 3 is your V1. V1 is the velocity at point 1 here, which is velocity at the reservoir. Basically we can put it also almost equal to 0 because we can look at the change over time here. The elevation change here basically meter per second is almost negligible. So because this is due to the big size of the reservoir, so when you want to compare with the V2, basically you will find out that the difference is very big difference, and you can assume that V1 is equal to 0 because the change here, the oil level here, when this one is run, we cannot see the changing, okay, here, because this is very minimum. And then I think we can put Z elevation here. So number 4, basically it already state here the elevation between station 1 and 2 basically is equal to 6 meter, right? So means that if this is your reference at point 1, so Z2 minus Z1 is equal to 6 meter. So this is a 4 term that you need to put into the Bernoulli equation here. So our objective is to find P2, okay, P2 as our objective. So now I will rearrange this equation. P2 over rho g equal to so this one V1 already 0, right? So it become HP HP plus Z1 minus Z2. Okay, and then you minus with V2 square over 2G, then you minus with HL. Alright, so in the equation also it already mentioned the value of HL, which is between station 1 and 2 is 9 meters, so no need to calculate it one more time. So I put number 5 here, HL equal to 9 meter. Right, so here we need to check what is the unknown parameter that we still not get here. So HP, we need to calculate it. Z1 or minus Z2 already get there. We have Z2 minus Z1, so this is just equal to minus 6. So V2 square, we need to find it, V2, and HL we already get in the equation. So we have two unknown here. You need to find HP and also V2. Okay, so now focusing to find HP, which is you can look back in the formula. Okay, HP, how to find HP? So just now I have put here, right, this is your formula to get the HP. HP equal to WP divided by rho GQ. Okay, so right here, HP equal to WP divided by rho GQ. So I always put this as a dot here to indicate the difference between energy and also power. Right, so in the equation it already gives you the value of the pump power, so just put the value here. Pump power basically is equal to 3730 watt divided by rho of the fluid, which is okay, it gives you specific gravity here, so you can convert it into density of the fluid. So in order to get the density here, so based on the formula come from the fluid mechanics, this is rho of the fluid, or you just put rho of the oil. So this is oil divided by rho on the base water, which is base fluid, which is water lah. Okay, so to get rho oil, you need to multiply Sg with the rho of the water. So I put here Sg oil multiply with rho of your water, and then you multiply with G multiply with Q. So what you will have just now, Sg is 0.9, rho of water we take 1000 kg per meter cube, G is 9.81 meter per second square, and your Q basically is equal to 0.001896 meter cube per second. Is that correct? Okay, Q 0.001896, right? So now just punch your calculator and you get the answer in meter. Okay, 3730 divided by 0.9 divided by 1000 0.81 divided by 0.001896. This is equivalent to 222.82 meter. So this is the pump head. Okay, so it can deliver the water as high as 222.82 meter. Right now, we need to find another one, which is V2. So in order to get V2, so you just back to the continuity equation, A1 V1 equal to A2 V2. So V1 actually is a velocity at the reservoir that we assume that it is almost equal to 0 because no change the velocity here. So now we just focusing on the state at number 2 because we want to find what is the velocity at station 2. So we just rearrange V2 equal to Q divided by A2. So this is equivalent to 0.001896 meter cube per second divided by pi multiply with the diameter square 0.02 square over 4. So make sure that the diameter that we use is a inside diameter. Okay, so outside diameter but doesn't applicable for this formula because the water basically drives through the inside diameter. Okay, so make sure this is a inside diameter. Yes, 0.02 meter. Okay, so you just punch your calculator and you get the answer in meter per second. So I get here the 6.035 meter per second. Okay, so all of the parameter already get. Then now you just put all of the information back here. P over rho G equal to, okay, so what is the HP? What is your HP? 222.82. Then plus Z1 minus Z2, which is minus 6 here, because Z2 minus Z1 is positive 6. So the opposite is minus 6 lah. Z1 minus Z2 minus V2 square, 6.035 square over 2G, 9.81, and then minus HL, so HL given as 9. Okay, so you get here 222.82 minus 6 minus 6.035 square divided by 2 by 9.81 minus 9. So I get here 205.96. Okay, so this is in meter, but now we just want the value of pressure, so you multiply with rho G. P equal to the rho of the oil. So rho of the oil basically equal to Sg oil times rho of the water. So need to multiply with the G and then multiply with 205.9 meter. So 0.9, 1000, 9.81, 205.9. What is the answer? So I get here 1818.5. Okay, so I get here right back 1818.453. So this is Pascal because we use all of the in SI unit. So this is a huge value, so I just change it into kilopascal. 1818.123.5 kPa. Alright, so this is the pressure at point 2. Okay, so because we rearrange the equation as P2 over rho G back. Okay, so this is the answer of the pressure at station 2. Okay, make sure you understand this because this is very important for the Bernoulli equation applied into the hydraulic circuit analysis. Okay, thank you very much. Assalamualaikum.